Okay, so in this video we are going to continue talking about the Standard Model. So far we've talked about 2 out of the 3 elementary particles. We talked about leptons to begin with, and we also talked about quarks. Okay, and so in this video we're going to wrap up talking about quarks, and then we'll kind of introduce the fundamental forces, and then the third type of particle, which are the gauge bosons. Okay, and so before we get to that, let's talk about something called quark confinement. Okay, so of course you can pause here and add this to your notes if you would wish. I'm just going to adjust the size so you can see it a little bit better. Basically, the idea behind quark confinement is that it is impossible to have an isolated quark. Okay, you cannot separate, let's say, a baryon or a meson and get just a quark by itself out there in the wild. So basically what happens is if you imagine taking, let's say, a meson and you try to pull a quark and an antiquark apart, because of the nature of the strong force that's holding those quarks together, you have to do work to cause that separation to happen. You have to put energy in order to pull those particles apart because they're held together. And it just so happens that in the case of quarks, at some point when you get enough energy in, rather than actually splitting the 2 quarks into individual pieces, you just end up taking that energy and creating a new quark-antiquark pair that forms. Okay, and so this is kind of a silly visualization of that process, I guess, where if you were to try to take, let's say this was a meson, and you tried to pull it apart, to end up with 2 individual quarks, you would end up just creating a brand new meson, because a quark-antiquark pair would be created from that energy that you're putting in to do the separation. And so that's the idea of quark confinement. You cannot have an isolated quark, and if you try to get an isolated quark, if you try to pull the quarks and something together, then you really just end up creating a brand new hadron, either a new meson or a new baryon. Well, I guess probably a new meson. Okay, so quarks have never been observed on their own, and this is basically just like a repeat of what we talked about before, where if you tried to take this meson, this is a down quark and an anti-strange quark. If you tried to put energy in to pull them apart, you would just end up creating a new meson pair. Okay, you would just end up creating a new down and anti-strange rather than the 2 individual quarks. Okay, so that's the idea of quark confinement. Okay, so let's move on and get to the third type of elementary particle, but first let's briefly review the 4 fundamental forces. Okay, so we've talked about these fundamental forces before, but according to current theories, or relatively current theories, within the last 40 or 50 years, there's only 4 fundamental forces in the entire universe. Those forces are the gravitational force, the electromagnetic force, the strong nuclear force, which is also sometimes called the strong interaction, and the weak nuclear force, which is also sometimes called the weak interaction. Okay, so of course we're very familiar with the gravitational force because we experience that on a regular basis. The electromagnetic force is one that we experience probably the most often in our day-to-day lives because we're all made of atoms, and those atoms are held together by the electrical forces. Molecules like in water, carbon dioxide, those are held together by those electrical forces. And so when you press on a wall and you feel the wall press back on you, that force is electromagnetic in nature. Okay, and so that is probably one of the most common forces that we experience in our day-to-day lives. And then we also have the strong interaction, which is responsible for holding together the nucleus. We've talked about this before, but inside the nucleus you have protons and neutrons, and the protons try to repel each other because of the Coulomb force. The Coulomb force, by the way, is, I guess you could kind of think of it as the electrical part of the electromagnetic force. And then the strong nuclear force that acts between both protons and neutrons is what holds a nucleus together. Okay, unless you have an unstable nucleus, okay, in which case you have something that's radioactive. And then the weak nuclear force is basically responsible for types of decay, okay, like beta decay that we've seen before. Okay, so we've talked about all four of these fundamental forces before, and what we're going to see then is that the last type of elementary particle, the gauged bosons, or what you could also call the exchange particles, are tied to these four fundamental forces. Okay, so it's important that you're aware of these forces. There's a lot of information in your textbook about these forces. Please do not write this in your notes because it's all in your textbook. I would make sure that you know the different properties of the different forces. But again, I would definitely not write all this down word for word. But you do need to know the relative strength of all of the four fundamental forces. You do need to know some basic facts about all of them. And so I would just kind of look over what's in the textbook and try to get down the most important information. Okay, so before we move on, I've got some videos I want you to see about the standard model. And these videos are just meant to help, put everything we've talked about so far kind of in context and in a way that's kind of easy to structure in your mind. Okay, so definitely check out these videos that I will put the link up for. Okay, and we're going to move on. So we've been talking about the standard model, of course, and the standard model has basically three types of elementary particles in it. Quarks, okay, 6 quarks, 6 leptons, and then of course, we've got the anti-quarks and the anti-leptons. And then what we call gauge bosons or force carriers or exchange particles. So those are all words meaning the same thing. Okay. So as far as we know, all known matter is composed of quarks and leptons, and those quarks and leptons interact with each other by exchanging particles called gauge bosons or force carrier particles or exchange particles. There's lots of different ways of naming that last one. Okay, but I will call them exchange particles. Okay, so let's talk about these exchange particles some more. Okay, so in the 1930s, a Japanese physicist, proposed a theory to explain the mechanism behind fundamental forces. Okay, basically, they were looking for an idea of, we know particles interact through these fundamental forces, but we don't have an exact mechanism for how that happens. And so according to his theory, he said that the force between any pair of particles is mediated, and when I say mediated, I mean transmitted, by particles called gauge bosons. Okay, that's the third type of elementary particle. Okay, and again, other names for these would be exchange particles or force carriers, basically because they are the particles that transmit those four fundamental forces. Okay, so for example, let's say you have 2 protons or 2 electrons in space. Okay, now we know, of course, that 2 protons are going to repel each other because they both have the same type of charge, just like 2 electrons are going to repel each other because of the same type of charge. Okay, and the idea is we know that, but how exactly does that work? Okay, and so according to this theory, if you have 2 protons and they're repelling each other, what Yukawa postulated was that the protons exchange exchange particles, but they exchange photons and repel each other because of this exchange of photons. And so basically, he's saying that the photon is the exchange particle for the force that protons repel each other through, okay, which is the electromagnetic force, or I guess more specifically the Coulomb force, which is just the electrical part of that force. Okay, so the analogy, I guess you could say, is let's say you had, 2 people each in a boat, and let's say each of these people represents a proton. By throwing this exchange particle back and forth and back and forth, okay, every time the exchange particle hits the other particle, it's going to cause repulsion. Okay, so if you imagine that analogy being true, okay, by exchanging this exchange particle, which in this case would be a photon, and then each of these people would represent a proton or an electron, depending on what you're talking about repelling. And by throwing this photon back and forth, that's how 2 protons know that, hey, I'm supposed to repel the other one. Okay. So that's the idea behind exchange particles. Okay, so turns out that each of the four fundamental forces has its own type of exchange particle. Okay, in this chart here, this is actually a really important chart for you to know. And so I would definitely write down the key elements of this chart in your notes. Relative strength basically compares the four fundamental forces to each other. That's important to know because in past years, sometimes they ask questions on the IB exam about, which of the fundamental forces are the strongest or the weakest. The weakest force is actually the force of gravity, which is kind of ironic because gravity is even weaker than the weak force. And notice that each of these four forces only affects certain type of particles. So for example, the electromagnetic force only affects particles that are electrically charged. Okay, so for example, two protons could repel each other through the electromagnetic force, but two neutrons could not. Okay, the exchange particle for the electromagnetic force is the photon, and it has an infinite range. Okay, so the photon is the exchange particle we talked about in the boat example. Other exchange particles are the graviton, which has not ever been observed, and you probably won't ever see an IB question related to the graviton because it has not been observed yet. That's still theoretical. The weak force actually has three types of exchange particles: the W plus, the W minus, and the Z. Okay, notice that the weak force only acts on quarks and leptons, and that is the force that governs particle decay. Okay, so when one type of quark changes into another type of quark, that results in a decay that involves the weak force. Okay, and then the gluon is the exchange particle for the strong force. And remember, the strong force holds quarks together. That's what's responsible for the stability of the nucleus. Okay, and that exchange particle is the gluon because it's like the glue that holds the nucleus together. Okay, I guess that's why it has its name. Okay, so by far the most common ones you'll see are the bottom three. I've never ever seen the graviton appear on an IB question because, again, that's still pretty theoretical. Also knows that the weak force and the strong force only exist within the confines of the nucleus. Okay, they both have a very short range force, whereas the gravitational force and the electromagnetic force have an infinite range. Okay, so everything on this chart you need to know. Okay, so I'm going to go to the next slide. I think this is basically just the same thing. It is important that you understand that anytime you see a quark change its type, that is an interaction via the weak interaction, the weak nuclear force. Okay, so when we talk about beta plus decay or beta minus decay, that involves the weak nuclear force. Okay, that is a fact that you need to know. Okay, so as we saw on the last couple of slides, you can think of all forces existing basically due to the exchange of these gauge bosons or the exchange of these force carriers between particles. Okay, these exchange particles are said to be virtual particles because they're not detected during the actual exchange. So in other words, two protons might exchange a photon back and forth between them as they repel, but we cannot actually observe that photon. And so, in that sense, it's like a virtual photon. Okay, now the last thing I want to talk about in this video, the Higgs boson, is something that you might have heard of before. I've got some videos that I want you to watch. The Higgs boson was discovered in 2012. It was theorized to exist since the 1960s by a guy named Higgs. A lot of the time you read about this in the media, and it's called the God particle, because basically it's the particle responsible for explaining why all other particles have mass. And so this was theorized to exist in the 60s, and it wasn't until relatively recently that it was actually discovered experimentally. Okay, so I want you to check out these two videos I'm going to link below about the Higgs particle. And then just to say, you also might have heard of, giant particle accelerators or things like the Large Hadron Collider, the LHC, okay, which is basically a giant giant region where they build these machines, and they basically cause particles to collide together. That's why it's called the Large Hadron Collider, because they're colliding hadrons. And when that happens, they see, like, a bunch of different tracks in their detection apparatus, and each of those tracks represents different particles. And by measuring, information about the tracks, they can figure out things about the mass and the energy of those particles. And so this is basically how we discover new particles. Okay. Although there is some debate about, how useful this is, as you can read through these little cartoons here. Okay, so that's all I want to say about the exchange of particles and the Higgs boson and all that. As always, please let me know if you have any questions, and I will see you guys in the next video.